16 billion miles from Earth, a machine built before the personal computer existed just sent home a signal that shouldn't be there. Not a malfunction, not static. A real measurable hum buried in the data, coming from a region of space every model said should be almost silent. And years after it was first detected, scientists still can't fully agree on what's causing it. This is Voyager 1's data, and this is a mystery that has been quietly unfolding since 2017, getting stranger with every new reading. Here's exactly what the signal is, why it breaks the predictions, and why the people studying it are still stuck between two competing explanations, neither one fully proven. I'm your host, and this is the channel that chases down the discoveries other channels rush past. If that's what you're here for, subscribe, because there's a lot more of this coming. To understand why this signal is such a problem, you first need to understand exactly where Voyager 1 is and how it got there. Voyager 1 launched on September 5th, 1977, on a mission that was never supposed to last this long. The plan was modest: fly past Jupiter, fly past Saturn, take pictures, gather data, then go quiet somewhere around 1981 or 1982. Instead, it kept going. It flew past Jupiter in March of 1979, capturing the first close-up images of that planet ever seen by human eyes. It flew past Saturn in November of 1980, using the planet's gravity to slingshot itself even further outward. And it just didn't stop. Then, on August 25th, 2012, 35 years after launch, Voyager 1 did something no human-made object had ever done before. It crossed the heliopause, the outer boundary of the bubble our sun's solar wind inflates around the entire solar system, and became the first spacecraft in history to physically leave the neighborhood of our star and enter interstellar space, the region between star systems. Not a symbolic milestone. An actual physical departure confirmed by a real drop in solar wind particles and a real jump in the density of surrounding plasma. And it kept transmitting the entire way through. That mattered enormously because, for the first time ever, humanity had a working scientific instrument physically sitting inside interstellar space, sending real data home. Every prediction ever made about what that region should look like had been built from inside our own solar system using telescopes, mathematics, and theory. Now, for the first time, something was actually out there, reporting back what it found. And what it found didn't match what anyone expected. Before Voyager 1 arrived, the leading models describing interstellar plasma, the extremely thin sea of charged particles filling the space between stars, predicted a fairly calm, quiet environment. Sparse, slow-moving, not much happening. A kind of cosmic waiting room between star systems. Then, starting in 2017, something strange began showing up in the readings from Voyager 1's plasma wave instrument. It wasn't a sudden spike. It wasn't a one-time event that could be dismissed as a glitch or a fluke. It was a persistent, narrow band of emission, a faint but steady hum, embedded in the plasma surrounding the spacecraft, showing up again and again, year after year, as Voyager 1 continued its outward journey. Researchers analyzing the data confirmed it in a peer-reviewed study. A genuine, weak, narrow-band plasma wave emission that has persisted in Voyager 1's readings continuously since 2017, detected across a stretch of interstellar space stretching tens of astronomical units, tens of times the distance between the Earth and the Sun. Here's why that mattered beyond just being unusual. Before this signal showed up, the only way scientists could measure the density of interstellar plasma at all was to wait for a shock wave. A burst of charged particles thrown outward by a solar eruption, traveling all the way past the heliopause and rattling the plasma out there like a bell. Those events were rare, unpredictable, and gave scientists nothing but scattered, disconnected snapshots, sometimes years apart. It was like trying to understand a country's entire climate by checking the temperature in one city. Once every few years, this new signal changed that completely. It wasn't triggered by anything happening on the sun. It was just there, quietly persistent, letting scientists take a fresh reading of interstellar plasma density roughly every few days instead of once every few years. For the first time in history, humanity had something close to a continuous real-time feed from inside interstellar space. And what that feed revealed was that the space between the stars isn't the smooth, sleepy void the old models predicted. It has texture. It has structure at scales from a fraction of an astronomical unit all the way up to tens of astronomical units. The turbulence detected wasn't a one-off anomaly localized to wherever Voyager 1 happened to be sitting. It was consistent, ongoing, and measurable across an enormous stretch of the spacecraft's journey outward. Now here's the part that still doesn't have a clean answer, years later. Scientists studying this persistent signal have narrowed the explanation down to two real possibilities, and as of right now, they still can't say for certain which one is correct. The first possibility is that this is what's called thermally excited plasma oscillations, essentially the natural ordinary vibration of plasma particles interacting with their surroundings. If this is the correct explanation, it would still be a meaningful discovery, revealing real structure and activity in interstellar space nobody had directly measured before, but it would fit comfortably inside existing physics. Nothing would need to be rewritten. The second possibility is something called quasi-thermal noise, a genuinely different physical mechanism, one that carries information about the density and temperature of interstellar plasma in a meaningfully different way than ordinary thermal oscillations do. If this turns out to be the correct explanation, some of the working assumptions scientists currently rely on to interpret readings from the interstellar medium would need real, substantial revision. The researchers behind the published findings were candid about this uncertainty, stating plainly that the possible mechanisms behind the narrowband emission include both thermally excited plasma oscillations and quasi-thermal noise, and that resolving which one is actually happening would require either new data from Voyager itself or an entirely new mission built specifically to study the interstellar medium up close. And here's the uncomfortable part of this story. There is no such mission currently funded. Nothing is currently underway to send another instrument out past the heliopause with the tools needed to settle this question definitively. If a mission like that were approved and built starting today, it would take decades just to reach the boundary Voyager 1 crossed back in 2012, let alone gather years of comparable data on the other side of it. Which means this open question, sitting unresolved in Voyager 1's data right now, may stay open for a very long time after Voyager 1 itself eventually goes silent. That silence is getting closer every year, and it adds real urgency to this mystery. Voyager 1 runs on power generated by radioisotope thermoelectric generators, essentially containers of slowly decaying plutonium converting heat into electricity. At launch, those generators produced around 470 watts. Today, nearly 5 decades later, that output has dropped dramatically, and it only ever goes down. There's no way to refuel it, no way to service it from 16 billion miles away. Because of that, NASA has spent years making increasingly difficult decisions about which instruments to keep alive and which ones to permanently shut off. Several instruments have already been switched off for good, not because they broke, but because there simply wasn't enough power left to keep running them. The plasma wave subsystem, the exact instrument responsible for detecting this unexplained signal in the first place, remains one of the few still operating. But every year, the list of active instruments gets shorter, and there's no undo button once one goes dark. So think about what that actually means for this mystery. Right now, the only working scientific instrument humanity has ever placed inside interstellar space is still recording the same unexplained signal it first picked up back in 2017. Nobody has definitively determined whether it's an ordinary plasma vibration or something that would force real revisions to how we understand the space between the stars. And realistically, we may not get that answer for a very long time. Not because scientists have stopped trying, but because the only instrument capable of gathering this specific kind of data is aging, losing power, and drifting further away with every year that passes. There's something worth sitting with here. This isn't a signal from something artificial. It isn't a transmission with intent behind it. It's a natural phenomenon in the plasma of interstellar space, and it's genuinely strange specifically because our models never predicted it should look like this in the first place. That's often how the most interesting scientific mysteries actually work. Not a dramatic singular anomaly, but a quiet, persistent piece of data that simply refuses to match the prediction year after year, forcing scientists to admit there's something about the universe they don't yet fully understand. There are questions about interstellar space that simply cannot be answered from a telescope on the ground, or a satellite in Earth orbit, or a probe orbiting Mars. They can only be answered from inside that environment itself, by an instrument actually sitting there, recording what's really happening. Right now, we have exactly one machine capable of doing that. It's nearly 50 years old. It runs on a few watts of power, less than the bulb in most refrigerators. And it's still, right now, sending back a signal we haven't fully figured out. The clock on that signal is running. Every year, less power. Every year, fewer instruments still active. And no second machine currently funded to pick up where this one eventually leaves off. If this is the kind of story you come here for, subscribe and turn on notifications. Because there's a lot more of the universe we haven't finished explaining. Drop a comment telling me which explanation you think is more likely. And share this with someone who needs to know that right now, nearly 50 years and 16 billion miles from home, an old machine is still listening and still sending back a question we haven't answered yet.